Okay, so we're starting a new chapter here. We're talking about the antiderivative or an antiderivative, and a common sense definition of an integral, which we're going to relate these integrals and antiderivatives later. But remember, the common sense definition of an integral, which we've talked about already, is just simply the area underneath the curve. In order to introduce the antiderivative, we're going to do a little bit of review of the derivative, and it's going to seem pretty basic. Remember the power rule when you're doing the antiderivative, right? If you start with this expression, you just subtract one from the exponent and multiply by the previous exponent. So as I look at this one down here, we could easily see, okay, the derivative of x cubed would be 3x squared. Pretty basic. Let's go to the next page though. And now, I know this is pretty basic, but I want you to just go ahead and take the derivative of these three things. There's something that we're looking for here. So go ahead and just do it on your own real quick, pause the video, and then come back when you're ready to continue. Okay, the idea that we're looking for here is we have three different functions. The only thing that's different about these three functions is the constant that we added at the end. This one has no constant, so it's 0, -3, and 97, but the derivatives are all the same. And this is an important thing to keep in mind when we start to learn about the antiderivative, right? So we would say capital, we usually use capital F for the antiderivative, so if there's some, if there's some function like 3x squared, right, then the antiderivative, which we already know because we just did this, would be x cubed. And so we say it's an antiderivative because really if you think about it, if we started here, it's really x cubed plus some c, right? See, if we reason through here, we have all these different original functions, and they're all antiderivatives of the same derivative we found 3x squared, right? So there's got to be some, if we started with this, right? If all we had was this information and we go to take the antiderivative, yes, it's x cubed, but there might have been, and most likely was, some constant there being added or subtracted to this function that we cannot find, that we do not know. And so we would just notate this as x cubed plus c. So this is why this is an antiderivative, because we don't really know what the antiderivative is until we can determine what this constant was. And that's because, remember, when you take the derivative constant, you just get 0. So let's go on to the next page. Okay, so let's just start off by saying we're going to find the antiderivative of the 6x to the 5th. But what I want to do is let's just say that this is f of x. So we have a way of talking about it. Well, that means then that the antiderivative, we would say that's capital F of x. And let's just think about this. We got a 6x, and we're going to add 1 to the exponent. So this is like 5 plus 1. And we are going to divide by this new exponent. That's the reverse power rule, if you think about it. It's the exact opposite of what we did when we took the derivative using the power rule. Well, obviously, this cleans up quite a bit. This is 6x to the 6 over just 6. And so these things cancel out. Now, I am forgetting something here, right? Because I really needed to consider the fact that there are an infinite number of constants that could have been added to this original function or to this antiderivative. And so my answer is going to be x to the 6 plus some c value, right? Because if this was, if this was, say, like a 4, and I took the derivative, I would still get 6x to the 5th. But if it was like a 213.579, and I took the derivative, I would still get 6x to the 5th. So this represents all possible antiderivatives of 6x to the 5th. All right, so I want you to try option B here on your own. Give it a shot. When you're ready to check your work, just unpause the video and see how you did. Okay, so we would add 1 to the current exponent, so it would go from 3 to 4. We'd also divide by the new exponent, so we would divide by 4, and we have to account for that constant. 2 divided by 4 reduces to just basically 1/2, or dividing by 2, so we have x over 4 divided by 2 plus c. That's all there is to it. All right, now let's play with a little bit different notation. Now we're saying the derivative is just simply 2, so what is the antiderivative? Well, the antiderivative here, since we already have y prime, we would just say the antiderivative is going to be y. And if you think about this, this is really like saying x to the 0. Essentially what it is. So when you add 1 to the exponent, you are simply going to make that x to the 1. And if you divide by 1, it's really just the same value. And then we, of course, are going to account for the constant. So what is this really? This is just simply y equals 2x plus c. And that makes sense because when we took the derivative of a linear equation, we had just a constant because a linear equation has a constant slope. So, seems to work out. All right. I'm going to help you get started on this one. Remember, a way to think about this one is not 1 over x squared. Don't think about some weird quotient rule, but think of this as x to the negative 2. Go ahead and give this one a try on your own, and we will, you can go ahead and pause the video and then check back when you're ready to check your work. All right, so we can see that if you were to take this negative 2 and add 1 to it, you would also have to divide by negative 2 plus 1. And so this becomes x to the negative 1 over negative 1 plus, of course, our constant, some constant. Well, this is really just negative 1 over x plus c. And so we have found that the antiderivative of this is negative 1 over x plus c. All right, let's go on to the next page. All right, what about when we're dealing with sine or cosine? Well, this is a really basic idea. We've already determined that we know the derivatives of sine and cosine. I'm just going to write them over here. Remember we said when finding the derivative, you just kind of work down this list. So the derivative of sine is cosine. Derivative of cosine is negative sine. Derivative of negative sine is negative cosine. And then, of course, it just repeats, right? Well, that means that the antiderivative just goes the opposite direction. That's it. We just have to account for the constant. So let's take a look at sine x. So the derivative of sine x is cosine x, but we want the antiderivative. So the antiderivative would be negative cosine x. So the antiderivative is negative cosine x plus some constant. Pretty straightforward. Go ahead and try B on your own. Pause the video, give it a shot. Okay, since the derivative of sine is cosine, therefore the antiderivative of cosine is simply sine. So that's all we get, sine x plus some c. Again, pretty basic idea here, not too challenging. Now we're going to get into some other trig functions, and these are ones that you just kind of have to recognize that these started off as derivatives, right? We know that secant squared here is the derivative of tangent. And so when we take the antiderivative, it's easy if you recognize that pattern that this is simply, the antiderivative is simply tangent of x plus some constant c. Okay, the next one is a little bit different. So what I'm going to propose is that because it doesn't fit our derivative that we know perfectly, let's just make it fit. Let's call this a negative cosecant squared x dx. And if we wanted to take the antiderivative of that now this is pretty straightforward because this is really just like a coefficient of negative 1. So with derivatives and antiderivatives, we can just leave coefficients out front and we could just focus on this. And so the antiderivative of this would be negative 1 times the antiderivative of negative cosecant squared, which is negative cotangent x. So this is negative 1 times cotangent x, plus some c value, of course. So we could clean this up just a little bit, and it would be negative cotangent x plus c. And that's really all there is to it. I'll see you guys in the next video.